So let's look at the snake lemma. So the statement is in any category, such as the category of any groups, or the category vector spaces or a given field, consider the computer diagrams as below. So this diagram is the most basic one. You have to make sure you have A, B, C, and this arrow G is surjective, and you have this A prime, B prime, C prime, F prime is injective. Okay? This is a basic setting. And then the result is there exists an exact sequence relating the kernels and the co-kernels of A, B, and C in the following form. Okay, start with the kernel of A. You can look at the diagram here, and then I wrote kernel of B and the kernel of C, and then a connecting map. It is written D here, and I prefer calling it delta. It's classical notation, such that you map it to co-kernel of A, co-kernel of B, co-kernel of C. This is the exact sequence. This is the first part of the result of snake lemma. And the second part is about the enforced version, which means if you all require this to be injective, F, and require this G prime to be surjective, then you will have more result telling you that then this kernel A to kernel B is injective and co-kernel B to co-kernel C is surjective. This is what is written here in the second part. This is the enforced version. Okay, so let's see how to prove this. So firstly, one important thing is you have to construct this connecting homomorphism delta. The way we construct it is by diagram chasing, which means let's take any arbitrary x here in kernel of C, small x. We're going to construct a map with image into co-kernel of A and call it delta of x. The way we construct it is as follows. You start with x, and then the image inside C, because this is kernel, so there's the inclusion. Let's still call it x. Okay, is inside C, and then we call this B to C surjective. That's why this is necessary. The basic setting must have this B to C surjective. Surjective implies there exists some element x prime. I would like to use all those x because tell me it related with x, comes from x. Okay, so you got this x prime B, which is mapped to C because it's a surjective map. And then if you look at the image under B of x prime, let's call it x double prime. And then now we know, observe that this x double prime is mapped to 0. And there will map G, because still call it F, call it G, or more precise call it F bar, G bar, and there G bar, because you have commutative diagram, x prime is mapped to its pre-image of small x. Small x is mapped to 0 because altogether this is 0 map. This is kernel of this map. And so x double prime is mapped to 0 and there your G bar. And so because this is the exact sequence, kernel of G bar equals image of F bar. So there exists, let's call it x triple prime. Okay, x triple prime pre-image, and then I'm going to define my delta x to be the quotient to this x triple prime because it's in the co-kernel. Or see, that's defined this delta. Now let's look at this given delta defined in this way gives you the exact sequence. So you have to check position by position basically. So how many positions are there? So let me directly prove the enforced version, supposing that already A to B is injective, which means small f is injective. Let's And let's suppose, so one important thing is that the first version actually tells you two version means that if you give something more on the basic version, you just require this f to be injective. It will give you enforced result, tell you that kernel B is injective, which is not in general true. And separately, if you require your G bar to be surjective, and then this will separately to give you enforced result that your co-kernel B to co-kernel C is surjective. Okay, which means you could, if you have both, you have both. If you only have surjectivity, you have surjectivity here. If you only have injectivity here, you have injectivity here, you have injectivity here in the kernel B. Okay, so let's check several positions. They are basically the same idea. Let's check first. This first position, kernel A to kernel B will be injective if your map from big A to big B is injective. So how do we check that? Check by definition. So suppose you have an element small x in kernel A which is mapped to 0. Then we want to show that it is already 0, and so this is injective. How do we do that? If x is mapped to 0, then you look at this image, enter this inclusion. I would like to still call it x, not x prime. Then this x by the quantitative diagram is still mapped to 0. Enter f. Right? This means that if we require this f already injective, then this small x must be 0 because it is mapped to 0. It is the kernel small f. If small f is required to be injective, then automatically this small x must be 0. And actually, that's all what we need. So, looks trivial, right? So let's look at the second position. So this position here, let's check this. Kernel G is better. Maybe let's just not to make confusion, let's call this kernel G and kernel F and kernel G. Not good notation. Let's just call it, distinguish with it. Let's call it F bar and G tilde, F tilde and G tilde. Okay. So we have to now check image of F bar F tilde equals kernel tilde. Basically, this is always true. Composition is 0 because this is just a subcomplex of this structure exact sequence big ABC. This one is just embedded into that, and so it is again complex. The composition of 2 will always be 0. In particular, this image F tilde is containing kernel G tilde. But what we don't know is that is this equality. So we have to check for whatever small x in this kernel B. I want to show there exists x prime in kernel A that is mapped to small x. Right? Put it more correct position. What we really want is start with element in kernel B. Can we find element in kernel A such that x prime is mapped to x? So still have to look at diagrams. Let's look at again this diagram. You start with your small element x in kernel B, But because by definition of kernel B, it is just if you map it vertically, you map to x, map to 0. But we now assume that this is small element x in kernel B is also mapped under G tilde to 0. And so if you look at this level, you know that because this x is mapped to 0 and this is a surjective map, short exact sequence, so there exists x prime that is mapped to this x. But then if you look at this x prime, if you look, it's mapped vertically, it maps x double prime here, right? And this x double prime by the commutative diagram, it must be mapped to 0 here, because x prime to x to 0, and so x prime to x double prime to 0, and so this x double prime is mapped to 0 in p prime. But here, this is essential. Here we require this map. So here actually we call it f bar. So we call this map, let's still call it f. This is injective map, so this implies this x double prime must be 0. And so this tells you that x prime is mapped to 0. And so kernel equals image tells you that, or because this is mapped to 0, so this x prime, the same x prime must be in the kernel A. And so x prime is mapped to x, tells you that this x prime is mapped to x. Because kernel is just an injective map into your just see it differently. So you regard your x as element of B, because you need the kernel, and then inside B you could find element in A that is mapped to x. But then this x prime, it is already in the kernel of A. Okay, and so x prime is mapped to x. So let's check, continue the third position here. So this is seems a little more complicated. You have to understand what is your map delta, and you have to check the kernel of delta is again the image of so here is G tilde, right? So you have to check the kernel. So you start with any element in kernel C, and you have to find an element in kernel B such that it is mapped to this arbitrary chosen x under G prime. So let's do that. And still, let's start with x. By definition, it is in kernel C. It is mapped vertically to x, and then it's mapped to 0. And because so basically you have to use the condition that delta x is 0. So delta x is 0 implies what? by our construction of delta x. So firstly, recall what is delta x. Delta x is what I've written here. Delta x is the image of x triple bar. The image of x triple is x triple bar. So that is 0. Implies that x triple is actually already in the image of A, which means there exists an element that is mapped x triple. If you look at this image and call it x4 force, just give it index 4, and you see its image under F. Let's give it index x5, and then this x5, this element is firstly by the commutative diagram. Its image will again be x double prime vertical, right? But recall we have x prime, who is vertical, is also x double prime. This tells you that this element and this element, their differences in the kernel of B. In particular, x prime minus x fifths is in the kernel of B. Another thing about x fifths is that it is mapped to 0. Horizontally, because it comes from x force. If you composing with 2 map, it's 0. So that doesn't hurt this image x, which means if you look at x fifths, let's come back here. If you look at your x fifths, whatever you map here, and then you work vertically, it will be 0. It will be your x. It will be 0 because x fifth is mapped to 0 vertically, horizontally, and so this part, whatever here, it will be mapped to 0, and hence we find the element in kernel B such that when you map first horizontally, then vertically, it's the same image as x prime, so the same image as x. So this element, which means its image compared with x, has the same image vertically, but this is an injective map. It tells you that they must be the same, which means this element, its image is again x. So we find a pre-image of x. The good thing is we don't know x prime is in kernel B or not, but this one is in kernel B. Lastly, let's say this position 6 and all those left ones. We have checked this 1, 2, 3, and this 4, 5 left you to check yourself, and the 6th one. Actually, very quickly, what you have to check is take whatever element in kernel C. Let's call it x. Does this G bar being surjective implies that should call this G bar actually. It's not good to call that G bar. That this G, let's call this F1, G1. Is F1 surjective implies this G bar surjective? This very quickly, this is yes, because if you got this surjective, to prove this is surjective, you just show that any x in kernel C there exists an element in kernel B whose image is x, right? But by definition of co-kernel, you just look at its pre-image in C, which means x is some x prime bar. So look at this x prime. Because this is surjective, we can find some x double prime, whose is pre-image of x prime. And the by commutative of this diagram, this x double prime will be mapped to some element x triple prime. By the commutative diagram, the x triple prime is one pre-image of x. So this is surjective.